Reactance is caused by the electromagnetic fields around current-carrying conductors. In separated overhead wires, the spacing between wires creates mutual inductance and capacitance, which contribute to reactance. Reverse phasing, by alternating the phase sequence between two sets of wires, reduces the mutual inductance between the phases, thereby reducing the overall reactance. Reactance increases the impedance of the circuit, which causes a voltage drop in the conductors. Reducing reactance by reverse phasing reduces the voltage drop, which improves the voltage regulation. The best configuration depends on the specific spacing and length of the wires. Generally, alternating the phase sequence between the upper and lower sets of wires, for example A, B, C, N on the upper set and C, B, A, N on the lower set, provides the most significant reduction in reactance. The reactance of a three-phase overhead line can be calculated using the following formula: XL equals 2 times pi times F times L, where XL is the reactance in ohms, F is the frequency in hertz, and L is the inductance in henries. The inductance of a line can be calculated using a formula that depends on the geometry of the conductors, including the spacing and length. The voltage drop, delta volts, along the line can be calculated using the following formula: delta volts equals R times I plus XL times I, where delta volts is the voltage drop in volts, R is the resistance of the line in ohms, I is the current in amps, and XL is the reactance in ohms. The same principles apply to the overhead wires connected to a backup generator. Reverse phasing can reduce the reactance and improve voltage regulation, especially over longer distances to the generator. Installing two sets of overhead wires in a reverse phasing configuration by alternating the phase sequence between the sets can significantly reduce reactance and improve voltage regulation in a residential area. The optimum configuration depends on the specific spacing and length of the wires, with A, B, C, N on one set and C, B, A, N on the other being a good starting point. Let's delve deeper into understanding reactance and how reverse phasing affects it in overhead power lines. Reactance, in essence, is the opposition to the change in current flow in an alternating current circuit. It's not a resistance which dissipates energy, but rather storage and release of energy in the form of electric and magnetic fields. Inductive reactance arises from the magnetic field created around a conductor when current flows through it. This magnetic field induces a voltage that opposes the change in current. Capacitive reactance, on the other hand, arises from the electric field between conductors. This electric field stores energy and opposes changes in voltage. In overhead power lines, both inductive and capacitive reactances are present due to the spacing and arrangement of the conductors. The spacing between the wires directly influences the magnetic and electric fields, and thus the inductance and capacitance. Wider spacing generally leads to higher inductance and lower capacitance, while closer spacing leads to lower inductance and higher capacitance. Now let's explore how reverse phasing comes into play. Reverse phasing involves arranging two sets of three-phase conductors in such a way that the phase sequence of one set is the reverse of the other. For instance, one set might have the sequence A, B, C, while the other has C, B, A. This arrangement has a significant impact on the mutual inductance between the conductors. When the phase sequence is the same, the magnetic fields produced by each conductor tend to reinforce each other, increasing the overall inductance. However, when the phase sequence is reversed, the magnetic fields tend to cancel each other out, reducing the overall inductance. This reduction in inductance directly translates to a reduction in inductive reactance. Similarly, reverse phasing can also affect capacitive reactance. The electric fields between conductors with opposite phase sequences tend to oppose each other, reducing the overall capacitance and thus the capacitive reactance. However, the effect on inductive reactance is generally more pronounced in overhead power lines due to the larger spacing between conductors. The reduction in reactance achieved through reverse phasing has several benefits. Firstly, it reduces the overall impedance of the power line, allowing for greater current flow with less voltage drop. This is particularly important in long transmission lines where voltage drop can be a significant issue. Secondly, it improves the power factor of the system. Power factor is a measure of how effectively electrical power is being used. A low power factor indicates that a significant portion of the current is being used to create magnetic fields rather than to do useful work. By reducing reactance, reverse phasing improves the power factor, making the system more efficient. Thirdly, it reduces electromagnetic interference or EMI. The cancelling effect of the magnetic fields in reverse phasing reduces the overall magnetic field strength around the power lines, minimizing the potential for EMI with nearby electronic devices. Let's consider the mathematical aspects of calculating reactance and voltage drop in more detail. The formula for inductive reactance, XL equals 2 times pi times F times L, highlights the direct relationship between reactance, frequency, and inductance. The higher the frequency of the inductance, the higher the reactance. The inductance, L, of an overhead line depends on several factors, including the diameter of the conductors, the spacing between them, and the length of the line. There are various formulas available for calculating inductance based on these parameters, often involving complex logarithmic expressions. The formula for voltage drop, delta volts equals R times A plus XL times I, shows that the voltage drop is proportional to both the resistance, R, and the reactance, XL, of the line. Reducing either R or XL will reduce the voltage drop. In the case of upgrading overhead lines, increasing the conductor size reduces the resistance, while implementing reverse phasing reduces the reactance. To determine the optimal configuration for a reverse phasing, several factors need to be considered. The spacing between the conductors, the length of the line, and the load current all play a role. Generally, a symmetrical arrangement with equal spacing between conductors is preferred. For example, arranging the conductors in a square or triangular configuration can provide good balance and minimize reactance. The specific configuration that provides the lowest reactance can be determined through calculations or simulations using specialized software. It's important to note that reverse phasing is not a perfect solution and may not be applicable in all situations. In some cases, the cost of implementing reverse phasing may outweigh the benefits. Additionally, reverse phasing can introduce some complexities in terms of system protection and coordination. Therefore, a thorough analysis should be performed before implementing reverse phasing to ensure that it is the most appropriate solution for the given situation. Now let's address the considerations for the backup generator. The same principles of reverse phasing apply to the overhead wires connecting the backup generator to the main grid. The longer the distance between the generator and the grid, the more significant the benefits of reverse phasing become. In this case, with an additional 130 meters or 425 feet of overhead wires, implementing reverse phasing can help to minimize voltage drop and improve voltage regulation. However, it's important to ensure that the reverse phasing configuration is compatible with the generator's protection system. The protection system needs to be able to detect and respond to faults in both the forward and reverse phase sequences. Additionally, the switching gear used to connect the generator to the grid needs to be properly configured to ensure that the phase sequence is correctly reversed. In conclusion, reverse phasing is a valuable technique for reducing reactance and improving voltage regulation in overhead power lines. By carefully considering the spacing, length, and load current, it's possible to optimize the configuration for maximum benefit. While reverse phasing is not a universal solution, it can be a cost-effective way to improve the performance and efficiency of power transmission and distribution systems. Firstly, consider the geometry. The physical arrangement of the conductors significantly impacts inductance and capacitance. Tightly bundled conductors reduce inductance, while increased spacing boosts it. Secondly, think about the transposition. Regularly swapping conductor positions along the line helps balance inductance and capacitance, minimizing imbalances. Thirdly, evaluate the conductor size. Larger conductors inherently possess lower resistance, directly reducing voltage drop alongside reactance mitigation efforts. Fourthly, look into insulation. Insulated conductors allow for closer spacing, which can reduce inductance, but the cost-benefit ratio must be carefully considered. Fifthly, reactive compensation devices can be used. Devices like shunt capacitors and reactors strategically placed along the line can counteract the effects of inductive and capacitive reactance. Sixthly, employ smart grid technologies. Advanced monitoring and control systems enable real-time adjustments to voltage and current, optimizing performance and minimizing losses due to reactance. Seventhly, regularly maintain the system. Keep connections tight, conductors clean, and vegetation clear to minimize losses and ensure optimal performance of reactance mitigation measures. Eighthly, consider upgrading to higher voltage levels. Transmitting power at higher voltages reduces current for the same power level, which in turn reduces losses due to reactance. Ninthly, focus on load balancing. Distributing loads evenly across the three phases minimizes neutral current and reduces losses associated with unbalanced reactance. And tenthly, implement power factor correction at the load. Encouraging or requiring consumers to improve their power factor reduces the overall reactive power demand on the system. Understanding the formulas is critical. Reactance, symbolized as X, arises from both inductance L and capacitance C in AC circuits. Inductive reactance XL increases with frequency F, calculated as XL equals 2 times pi times F times L. Capacitive reactance XC decreases with frequency, calculated as XC equals 1 divided by 2 times pi times F times C. Total reactance is the difference between these two. The impedance Z is the total opposition to current flow, combining resistance R and reactance, calculated as C equals the square root of R squared plus X squared. Voltage drop, delta volts, is directly proportional to impedance and current I, calculated as delta volts equals I times C. Power factor, PF, represents the ratio of real power to apparent power, calculated as PF equals R divided by Z. Lowering reactance improves power factor, reducing losses and improving efficiency. Mitigation strategies target these variables. Minimizing L and C reduces X, using larger conductors lowers R, decreasing Z. Balancing loads equalizes current across phases, minimizing neutral current and associated losses. Careful calculations using these formulas are essential for effective reactance management. Consider the environmental factors. Temperature variations affect conductor resistance, influencing voltage drop and losses. Humidity and pollution can degrade insulation, increasing leakage current and reducing system efficiency. Wind loading can cause conductor sag and sway, altering conductor spacing and potentially increasing reactance. Ice accumulation adds weight to conductors, increasing sag and stress, and potentially damaging insulators. Soil conditions affect the grounding system's effectiveness, influencing fault current flow and system protection. Vegetation growth near power lines can create safety hazards and increase the risk of outages. Wildlife activity can damage equipment and cause faults. Regular inspections and maintenance are crucial to address these environmental factors and ensure reliable system operation. Remember that safety is of utmost importance. Always to energize equipment before working on it. Use appropriate personal protective equipment or PPE, including gloves, eye protection, and flame-resistant clothing. Follow established safety procedures and guidelines. Be aware of potential hazards such as arc flash and electric shock. Maintain a safe working distance from energized equipment. Never work alone. Have a qualified observer present who can provide assistance in case of an emergency. Report any unsafe conditions or practices to your supervisor. Stay informed about the latest safety regulations and best practices. Attend regular safety training sessions. By prioritizing safety, you can prevent accidents and ensure a safe working environment. It's also important to consider the long-term economic implications of reactance mitigation strategies. While initial investments in larger conductors or reactive compensation devices may seem costly, they can result in significant savings over the lifetime of the system due to reduced losses and improved efficiency. A thorough cost-benefit analysis should be performed to evaluate the economic viability of different mitigation options. This analysis should take into account factors such as the cost of equipment, installation costs, maintenance costs, and the value of energy savings. Additionally, it's important to consider the environmental benefits of reduced energy consumption, such as lower greenhouse gas emissions. In some cases, government incentives or tax credits may be available to support the implementation of energy-efficient technologies. By carefully considering the economic and environmental implications, you can make informed decisions about how to best manage reactance in your power system. It's crucial to stay updated on the latest advancements in reactance mitigation technologies. New materials, designs, and control strategies are constantly being developed to improve the performance and efficiency of power systems. For example, high-temperature superconducting cables offer the potential to significantly reduce resistance and reactance, enabling the transmission of large amounts of power over long distances with minimal losses. Smart grid technologies, such as advanced metering infrastructure and distribution automation systems, provide real-time monitoring and control capabilities that can be used to optimize system performance and reduce reactance. Furthermore, research is ongoing to develop new reactive compensation devices that are more compact, efficient, and reliable. By staying informed about these advancements, you can identify opportunities to improve the performance and efficiency of your power system and reduce the cost associated with reactance. Consider the integration of renewable energy sources. The increasing penetration of renewable energy sources, such as solar and wind, presents new challenges and opportunities for reactance mitigation. Renewable energy sources are often located far from load centers, requiring long transmission lines that are susceptible to voltage drop and losses due to reactance. Additionally, the intermittent nature of renewable energy sources can cause voltage fluctuations and power quality issues. To address these challenges, advanced reactive compensation devices and control strategies are needed to stabilize the grid and ensure reliable operation. Smart grid technologies play a crucial role in integrating renewable energy sources by providing real-time monitoring and control capabilities that can be used to manage voltage and frequency fluctuations. Furthermore, energy storage systems, such as batteries, can be used to smooth out the output of renewable energy sources and provide grid support services. By carefully considering the integration of renewable energy sources, you can ensure that your power system is able to reliably and efficiently deliver clean energy to consumers. Finally, remember that reactance mitigation is an ongoing process that requires continuous monitoring, maintenance, and optimization. As load patterns change, new technologies emerge, and environmental conditions vary, it's important to regularly reassess your reactance mitigation strategies and make adjustments as needed. This may involve upgrading equipment, reconfiguring the grid, or implementing new control strategies. Regular inspections and maintenance are essential to ensure that equipment is operating properly and that connections are tight. Data analytics can be used to identify areas where reactance is causing problems and to evaluate the effectiveness of mitigation measures. By taking a proactive approach to reactance mitigation, you can ensure that your power system remains reliable, efficient, and cost-effective over the long term. Remember, a well-managed power system is essential for supporting economic growth, improving quality of life, and protecting the environment.